Okay, so friend, today we are going to study the symmetrical components in power system 2. So you can see the definition. A three-phase system is said to be symmetrical when the system viewed from any phase is similar and self-impedance of all the three phases are equal. Now if I give a simple example, then this would be, so this is a three-phase system, and this, if it is x x x, so this system, the self impedance when viewed from any phase is same. So system can be said to be in symmetrical. Symmetry means in general you also know it should be same from both the sides. Symmetry across, here in this case it is across your y-axis, symmetry about y-axis, so such is the phase. Now a very important theorem is there for Teske's theorem. So the Fortescue's theorem says that an unbalanced set of n phasors may be resolved into n minus 1 balanced n phase system of different phase sequences and one zero sequence. Say if we are taking a three-phase system, VA, VB and VC, so these can be resolved into n minus 1, that is 3 minus 1 equal to 2 balanced, that can resolve into two balanced phase system of different phases. So VA can be resolved into VA plus VA1 plus VA2 plus one zero sequence. Here we have mentioned plus one zero sequence system, that is VA0. Similarly B can be resolved and similarly C can be resolved. So another way of defining is, for Tesky theorem, is the three-phase unsymmetrical. So another way of defining it is the three-phase unsymmetrical and unbalanced phasor. It can be voltage or current phasor that can be resolved into a three components with positive phase sequence. Second is negative phase sequence, and third is zero phase sequence. So it can be resolved into these three components. That is, already I have written VA is equal to VA0 plus VA1 plus VA2. Similarly, VB is equal to VB0 plus VB1 plus VB2, and likewise VC0 plus VC1 plus VC2. So this can be resolved into three components. Now there is two, again there are two concepts. First one is your component analysis. And second thing is component synthesis and component analysis. Okay, now let us first look at component synthesis. So determination of the original phasor in terms of in terms of the sequence components. That is called as your component synthesis. So in other words, simply from VA0, VB0, VC0 and VA1, VB1, VC1, and similarly VC0, VC1, VC0, and this is VA2, VC2 and VB2, and this is VC2. So with the help of this, when we are trying to synthesize our original phasors, that is VA, VB and VC, then this process is called as your component synthesis, and the analysis is just the opposite of that. So the determination of original phasors in terms of sequence component is called as component synthesis, and use is made of alpha operator to express each of the components of VB and VC in terms of components of VA. That is, now we are taking VA as a reference, you can say. Okay, and in terms of VA, we are trying to in terms of VA and its components, sequence components, we are trying to write other phasors, that is phasor B and C, in terms of VA. So that is what we have written above. Okay, now let us see how to do that. Now let us consider one unbalanced phasor. So this, let it be VA, this is say VC, and this is your VB. So this is your unbalanced phasor, because you can see the angles, these are not having any relation, and that is why this is a unbalanced system. Now again, say this is your VA1, this is your VB1, and this is your VC1. So they have a phase difference of 120 degree. Now they have phase difference of 120 degree. That means it is a balanced system, first of all. Now second thing we observe is, as you see, when you are moving in a clockwise, then we have A, then B, and then C. That means this is clockwise, and therefore this is referred to as positive sequence. Okay, so in alternators, the coils are arranged in a particular fashion. So if they are connected in this fashion, then that would be a positive sequence, that is clockwise. Now another can be drawn. So here you can see again the system is a balanced one, but the sequence has changed. A, C, B, and that means they're moving in anti-clockwise direction, hence this is a negative sequence. So this is positive sequence, this is negative sequence, and the first one was your unbalanced system. Now what if we are drawing a zero sequence? So in zero sequence you can see your VA0, VB0 and VC0. This is D, this is zero sequence. They're equal for all the three phases or all the three phasors. They're equal for all the three phasors. Now from referring to the figure B, from figure B, that is your positive sequence. So from the positive sequence we can see, from positive sequence if you see, then CDB, this is the phasor B, and B here is lagging, or you can say VB lags VA, this angle here, VB lags VA by 120 degree, and that means alpha is equal to your 1 at angle 120 degree. This implies alpha square is equal to 1 at angle 240 degree, and this is equal to 1 at angle minus 120 degree, and therefore we can write VB1 is equal to alpha square VA. And similarly, sorry, this is not required, this angle, again this is 120 degree. So similarly for VC1 we have VC1 is equal to 1 at angle 120 degree into VA. So from there we get VB1 is equal to this and VC1 is equal to this. Now from negative sequence, we get is VB1 is equal to, sorry, this is VB2. VB2 is equal to alpha VA2, and VC2 is equal to alpha square VA2. So here it is this. Now from the above two equation, let this be 1 and let this be 2, hence we get VA is equal to, you already know from Fortescue, VA0 plus VA1 plus VA2, and from Fortescue's theorem. And VB is equal to VB0 plus VB1 plus VB2, but this is equal to VA0, and this is equal to, from equation 1, alpha square VA1, and this is equal to alpha VA2. So finally we are getting is this. So, and likewise for phasor VC we have VC0 plus VC1 plus VC2, and this is nothing but VA0 plus V, this is alpha VA1 plus alpha square VA2. So this is and this. So this is equation 3, or in matrix form we can also write these three equations: VA, VB and VC. This can be written as, here it is 1, 1 and 1. This is your VA0, VA1, VA2. Now this is always 1, and here now this is alpha square, this is your alpha, this is alpha, and this is your alpha square. This will be equation 4. Or simply VABC is equal to matrix A into V0, 1, 2, where 0, 1, 2 represents the sequence components, and these are the original phasors. So these are the original phasors and these are the sequence components, and the matrix, this is your matrix A, where matrix A is given by 1, 1, 1, 1, 1, alpha square alpha, and this is alpha, alpha square. And this matrix is called as symmetrical component transform matrix. So this was all about your component synthesis. Now the next topic we would see is your component analysis. This is your component analysis. So the determination of sequence components in terms of the original phasors, that is called as your component synthesis. We have already seen that VABC is equal to matrix A, that is sequence component transform matrix, into your V0, 1, 2. Now what we require is, we require in analysis is your V01. So just going by the mathematical approach of matrices, this is, so what we have to find is V0, 2. Okay, now what we'll do, VABC, take the inverse of that. This becomes equal to A inverse A V0, 2, and this will give A inverse is equal to, you have to find A inverse, and directly with the help of calculator you can find the A inverse, and that you will get 1, 1, 1, 1 1. Remember that this is always 1 in both the cases, and here only the thing would change is that is alpha, this becomes alpha square, this become alpha square, and this become alpha. Okay, and a multiplication factor of 1 by 3 comes into existence. So inverse using calculator you can do, or also you can solve it manually by taking the adjoints and cofactors, but it won't be much difficult to solve. Now alpha is equal to, we know that 1 at angle 120 degree. So from there we get VA0, VA1, VA2. This is our sequence components. This is our sequence components, and that is equal to 1 upon 3, 1 1 1 1 1. This is alpha, this is alpha square, this is alpha square, this is alpha, and you have VA, VB, VC, and these are your original phasors. And this is only your component analysis. So this is your component analysis. Now so let us say write VA0, that would be 1 by 3 VA plus VB plus VC. Similarly VA1 would give 1 by 3 VA plus alpha VB plus alpha square VC, and VA2 would give 1 by 3 VA plus alpha square VB plus alpha VC. So this is what we get. Let this be equation 5. Now for current, make a note that for current same procedure can be obtained, because V or I, that is basically a phasor. Okay, so this was all about your phase sequence. Now from in next video we'll see the various applications of these sequence and for Fortescue theorems, and also we'll solve some numerical. For this video we end here. Thank you.